Okay, so I decided that I'm going to combine the review of redox and the use of reduction potentials and those problems with the calculations of delta G associated with the chemiosmotic process. So there will be only one problem video for this discussion of the electron transport chain. So remember, we just saw a few moments ago a table of reduction potentials, and these can be used as a measure to predict, or they are a measure of a substance's tendency to accept electrons, but also can be used to predict which substance in a reaction will be oxidized and which will be reduced. So what we have here is a diagram of a vat that contains Fe3 plus that is easily reduced to Fe2 plus, and copper 1 plus that can be oxidized to copper 2 plus. So in this setup, we have two pieces of platinum in each of these vats. We have a salt bridge that connects the solutions that are present. The platinum is inert, so it doesn't actually play a role in the reaction. However, it will accept the electrons, and those electrons then are transferred through a voltage meter, which measures the voltage that occurs within this transfer of electrons. So in a table of reduction potentials, I can look up the reaction or the reduction of Fe3 plus to Fe2 plus, and that standard E of reduction equals a positive 0.77 volts. And remember, the more positive the reduction potential is, the more likely that one will be reduced. I look up the same for the reduction of copper 2 plus. And again, these are all written as reductions, not oxidations. And that E of reduction is a positive 0.15 volts. So based on the size of these potentials, the fact that Fe3 plus, or the E of reduction, is greater than the E of reduction of copper 2 plus, Fe3 plus will be reduced, and Cu plus will be oxidized. So, in order to calculate the E of this cell, which is what we would call this, we will combine those two reactions as a reduction and an oxidation. Since iron is going to be reduced, we're going to write this as an E of reduction, and that is a positive 0.77 volts. And because we are flipping this equation, we're going to be oxidizing copper, we will be changing the sign on that reduction potential so it reflects the E of oxidation. So now this becomes a negative 0.15 volts. So the E of this cell equals 0.62 volts. So just to review once again, I've just said this, but I'm going to flip to another piece of paper here. So those standard reduction potentials, so that E with that superscript naught, are always written as reduction reactions. So when you look at a table of reduction potentials, you'll see them as reduction reactions. The larger, positive potentials. So those elements or molecules with the large positive potentials have a strong tendency to gain electrons or be reduced. And they are strong oxidizing agents. I can squeeze that in there. And because of that, or alternatively, the large negative potentials, or those with large negative potentials, have a strong tendency to give up electrons. Or be oxidized. And thus these are strong reducing agents. So if something is oxidized, it's a reducing agent. If something is reduced, it's an oxidizing agent. As I squeeze that in there. So we have an example here. We've got a reaction from the citric acid cycle that we just looked at previously, or prior to electron transport chain. So we're going to look at the reduction of NAD, which requires 2 electrons, or NAD+, and 2 protons. And NAD is reduced to NADH plus a proton. The standard E of reduction here is negative 0.32 volts. And now I'm going to look at the reduction potential of alpha ketoglutarate. One of our intermediates in the citric acid cycle. So alpha ketoglutarate plus CO2 plus 2H plus 2 electrons gives me isocitrate. And the standard E of reduction here is a negative 0.38 volts. Now, because the reduction potential of NAD, or NAD+, at negative 0.32 volts is less than the E, or standard E of reduction, of alpha ketoglutarate. I'm just going to shorten that, which is a negative 0.38 volts. That means NAD+ will be reduced. And that is exactly what happens. And to calculate the energy of that reaction, we will combine these two but change the sign of the reduction potential of alpha-ketoglutarate from a negative to a positive. So now when I pull this together, I'm going to rewrite the reactions. This one is still negative, but I need to flip the alpha-ketoglutarate reduction reaction. And when I do that, I'm going to change the sign of the reduction potential to a positive. And I don't have room to write that positive potential in the same line, so I'm going to write it here. So now, oops, where are my, here we go. Colored pens here. So now we can cancel anything that appears on opposite sides of the equation between these two. So we can cancel 2 electrons, we can cancel 2 hydrogen ions, and when we do that, we will come up with the overall reaction that gives us isocitrate and NAD plus with alpha-ketoglutarate plus CO2 plus NADH plus H plus, and I get an E, or a standard E of this reaction, as a positive 0.06 volts. So when the standard E of any reaction or cell is positive, that reaction is spontaneous. So this is a spontaneous reaction. We can also calculate delta G, or the free energy of a reaction, and we'll do some examples there. But I'm going to give you, actually I think I'll switch to a clean sheet. Give you that overall equation, and that is the standard change in standard free energy equals negative N, which is number of moles, times the Faraday constant, times the change in the E of the cell. And actually, I should have perhaps put a change here, because that is the change. Okay. So we can calculate the standard free energy for the reaction that we just looked at. So the standard change in standard free energy for this reaction is a negative. I'm sorry, I should clarify. This is the number of moles of electrons, of which we had 2. So there were 2 moles of electrons that were transferred in this reaction. So there's that 2. The Faraday constant is 96,485 joules per volt mole. And our change in E of that reaction is a 0.06 volts. So, excuse me, here we have moles. Moles will cancel, volts will cancel, and we'll have the standard free energy of this reaction in joules. And I have reported this in kilojoules, and that is a negative 11.58 kilojoules per mole. Now remember, when del G's are negative, that is also indicative of a spontaneous reaction. Delta G is positive, it is non-spontaneous. Now, one thing I want to point out is we're using the standard free energy. Again, that's indicating we're at standard free energy. So that means that this calculation reflects this reaction under standard conditions. And under standard conditions, reactants are 1 molar. So the concentration of reactants are 1 molar. However, the free energy changes in a cell occur under non-standard conditions. The solutions in our bodies and cells are not 1 molar. So we have to modify this equation to account for that. And that equation is E equals the standard energy minus RT. R is a gas law, or gas constant, temperature, and that is divided by the number of moles of electrons times the ln of what the substance that is oxidized divided by the substance that is reduced. This can be simplified a little bit because these three things will be constant, essentially, in a cell, and that works out to be 0.0257 volts divided by N, which is the number of electrons, times the natural log of the ratio of oxidized to reduced. Okay, let's do another one. So, this problem states that for sorry about that, I had my phone muted, but it still rang for some reason. So for every 2 QH2, which you will see in the electron transport chain, that enter the Q cycle, one is regenerated, and the other passes 2 electrons to cytochrome C centers. and we want to find what is the change in the E of that reaction. So the overall equation is QH2 plus 2 cytochrome C1s, which are associated with Fe3 plus, or which contain that redox center, give us Q plus 2 site C and with an Fe2 plus and 2 protons. So I look up the reduction potentials for the two half reactions. So for the reduction of cytochrome, C1, Fe3 plus 1 electron, we get cytochrome C1 reduced to Fe2 plus. And the standard E of reduction is 0.22 volts. When I look up the reduction of Q, we have Q plus 2 protons plus 2 electrons to produce QH2 with a standard E of reduction of 0.045 volts. So the more positive E of reduction is going to be reduced, and the smaller will be oxidized. So this will be reduced, and this one will be oxidized. So as I rewrite these, I'm going to flip the second equation. So I'm going to write the site C1 as is, because this is reduced. And it's E of reduction, or standard E of reduction, 0.22 volts. This one gets flipped because we are oxidizing. Wait a minute. Sorry, didn't need that. So E of oxidation is a negative 0.045 volts. So I'm going to add these two together to come up with that overall reaction, canceling anything that I can. However, we also have to do one more thing. We have 2 moles of electrons in the oxidation of QH2 and only 1 mole in the reduction of cytochrome C with a Fe3 plus. So I need coefficients of 2. So this we need to multiply by 2. However, unlike delta H, if you think back to your Gen Chem 1, we do not treat the reduction potentials or oxidation potentials in the same way by multiplying them. They are not multiplied. So now all we have to do is cancel our electrons and add these reactions together, and we get QH2 plus 2 site C1 with an Fe3 plus, going to the oxidized version, plus 2 site C1s Fe2 plus, and our standard E of this reaction then will be 0.175 volts, which is also spontaneous. Did I miss some hydrogens? I missed 2 hydrogens there. Sorry about that. Missed these guys. So this is the change in the standard potential of that reaction. So what if we were asked, oh wait, that's not the one I want to do. Now we're going to switch to the standard free energy associated with the chemiosmotic process. So we are going to calculate this change in the standard free energy for the oxidation of malate. Again, another citric acid cycle intermediate. So oxidation of malate by NAD+, so NAD+ is reduced. And then we want to specify or classify if it's spontaneous or non-spontaneous. Keeping in mind that a negative delta G is spontaneous and positive delta G is non-spontaneous. Okay. So we're going to, number 1, write the half reactions or the reduction potential reactions. Whoops. And for oxaloacetate, oh wait, I jumped ahead of myself. Oh. Okay, yeah, right. Never mind, I confused myself there for a moment. So the oxidation of L-malate results in the production of oxaloacetate. So I need the reduction reaction of oxaloacetate, which again I'm getting from a standard reduction table. And the E of reduction for this reaction is a negative 0.166, and these are all in volts again. The reduction potential for NAD+, oops, what did I do here? Yeah, I need to. To give NADH, and this is +1 hydrogen, and that reduction potential is a negative 0.315. So NAD plus will be reduced. And oxaloacetate will be oxidized. Okay, so I want to point out, whoops, get the focus back here, that if we looked at the standard reduction potentials, the reaction would not occur with the oxidation of malate, but we're asked to calculate that. So that is to prove that the reaction does not occur this way, essentially. If we look at the reduction potentials, the reduction potential of NAD is far more negative than that of oxaloacetate. But we're asked to calculate this for the oxidation of malate. So that means that we are going to flip the equation, the reduction equation for NAD+. So when I rewrite these, whoops, no, said that wrong. We are going to oxidize malate, so we're going to flip this one. So we have malate being oxidized to oxaloacetate. I need to get my 2 H pluses plus 2 electrons. And then our standard reduction potential, I'm going to have to write it down, or oxidation potential, becomes a positive 0.166 volts. And NAD plus 2H plus 2 electrons gives me NADH plus hydrogen ion. And this E of reduction equals a negative 0.315 volts. So when I sum these, I can cancel, my hydrogens, ions, my electrons, and the overall reaction then would be malate plus NAD plus, giving us oxaloacetate and NADH plus H plus. And the change in that reaction is a negative 0.149 volts. So this would be non-spontaneous. Thus, we require, thus it does not work in the opposite direction. It will be only in the forward direction where I'm sorry, I'm screwing this up. But based on reduction potentials, it doesn't work that way, and that's due to the enzyme. Sorry. Every time I look at this particular problem, and I look at the reduction potentials, I get a little thrown off. So, read your questions carefully and follow up appropriately. So one more problem, and that is calculating the delta G for this problem, which shows it is non-spontaneous because that delta G is going to be positive. Sorry, let me straighten that up there. So when we calculate the delta G for this reaction, or the standard change in free energy, that is negative N times the Faraday constant times the change in E that we just determined. So the standard change in standard free energy is minus 2 moles of electrons times the Faraday constant. These equations and constants will be given to you. You do not need to know them. Times the change in E, which is a negative 0.149 volts. So it gives us a positive 28,750, joules. Which is a non-spontaneous reaction. So spontaneous. So to follow up on that, in vivo or in the cell, this non-spontaneous reaction in the TCA cycle, which is number 8, is coupled to reaction 1. Which is spontaneous.